Hi everyone. So this is the first time I've tried this, so please bear with me. I've made a PowerPoint for you and I'm going to try and talk through it. So it's for 13.2, more about resistance, because I've asked you to do some work in 13.1 before. So yeah, the first slide is here, and it is a asked you to spot the difference. So when the switch is closed here, obviously a current flows through the wires. And within the wires you can see the delocalized electrons and the fixed ions here. And hopefully what you can see between the difference between the two is the cool wire. When the switch is closed, the fixed ions only vibrate a small amount. But when you have the hot wire, the fixed ions vibrate with a greater amplitude, which means that the rate of the current flow, so the rate of flow of the charge here, is slower in the hot wire. So the learning objectives for 13.2 are: you need to be able to define resistance heating, be able to calculate resistance in series and parallel, and be able to calculate the current and potential difference for each component in a circuit. So looking back at this picture, or this GIF that we had before, you can see here a static version where you've got the positive metal ions and then the sea of freely moving negative electrons. It's called a sea because there's a lot of them. Okay. So resistance causes heating. That's because there's a movement of electrons through the wire, which is the current. And then in metallic bonding, there are delocalized electrons, which are these, which have come from the outer shell of the metallic elements. As if it was gold, you would have some of the gold electrons will have been removed from the atom. Sorry, one moment. Yes? Yeah, you need to get it there, okay. Go and get them then. Okay. Sorry, the pressures are working from home. So yeah, when you remove these outer electrons, they leave behind the positive ions, which are fixed in place here. So they can move, they vibrate, but they can't move position. Then when the delocalized electrons collide with the fixed ions, they transfer kinetic energy to into thermal energy, and the temperature of the wire then increases. Okay. Once the electrons stop still, it needs to get moving again, and because there's a potential difference across the metal or the material from the cell here, that forces the electrons to move again, and so that will then create more collisions. And then the amplitude of vibration of fixed ions increases, causing the rate of collision to increase, and the resistance to current flow will also increase then. So here's a question I want you to have a little go at. Okay, so it's got define resistance, it's got going to sketch a graph, and then want you to write your answer here, and then on the next slide you'll be able to mark it. Okay, try it without marking it, do it, and then correct it in purple pen. Right, next we're going to look at resistors in series. This is GCSE level, but I mean it's helpful to have a good another look at it. So I've got a wire here, it's carrying 1 milliamp of current, 3 resistors in series, 1000, 2000 and 6000 ohms, and then the ratio of the voltages here are 1, 2 and 6 volts. So then that's 9 volts in total across all the resistors. So the total potential difference is the sum of the potential difference across each resistor. Because they're in series, they're sharing that potential difference. The current has to, if you think of the current, like I've said before, as soldiers. So the soldiers are walking, which is the current, and then they're carrying the potential difference, which are like bullets, and they have to give it up. So if each electron's carrying 9 bullets, to get through these resistors, they'd have to give 1 to this one, 2 to this one, and 6 to this one to get through, okay? And then in total that would be 9 volts. The current's the same because there's only one pathway for the current to flow through, so that's 1 milliamp. Now this is Ohm's, well, a rearrangement of Ohm's law, so the potential difference is equal to the current times resistance. So the total potential difference across all of them is the potential difference across one, across the second one, and then across the third one. If we substitute this in for each of these, okay, we can see that the current is the same, and then you've got resistance of R1. Then for the second potential difference, you've got current, which is the same, and then that resistance, and then the third potential difference will be the current times that resistance. Now the total resistance in the circuit, okay, if we rearrange this into Ohm's law, the total resistance of the circuit will be the total potential difference divided by the current. So for this VT, I'm going to substitute in this equation here that I've created there, and then divide by the current. And as you can see, all of those currents are then going to cancel out. So you'll get the total resistance is equal to R1 plus R2 plus R3. Okay, so this is a proof of this rule. Okay, so if you get asked to prove it, this is the process you go through these two things. In our example, we've got 1,000, 2,000 and 6,000 ohms, add them together, 9,000. So very simply, for resistors in series, the total resistance is equal to the sum of the individual resistances, R1, R2 and R3, and however many you've got. Now resistors in parallel, you do study at GCSE, but you only study the fact that when you add resistors in parallel, the resistance goes down. You don't actually do the equation. So you have to do the equation for A level. So I've got two resistors here, 1 and 2. I've got a potential difference of 12 volts. I've got a current here, total current, which then splits because they're in parallel. If you think about the soldiers walking around, some of them will walk this way, some of them will walk this way. And more will walk this way because the resistance is less. Okay? Then they join back together here and then go up here. So, if we think of across each of these branches then, they will get the same potential difference. So all the electrons that go this way give all their 12 volts to this resistor. And all the electrons that go this way give all their 12 volts to this resistor. So it's the current that's different, the voltage is the same. So the total current in the circuit is the sum of the currents in each branch. So if I wanted to get IT, I'd have to gather the total current, I1 plus I2. So, since current is equal to potential difference divided by resistance, the current in resistor 1 here will be the voltage across it, which in this case is 12, divided by its resistance. And then in the second one, the current in this one will be the voltage across it divided by its resistance. The total current is the sum of the current in each branch. So IT is equal to I1 plus I2. So you've got that there. And then if you substitute this in here for I1, there, and this here for I2, there, you get this. And that will equal I total, which will be the total voltage divided by the total resistance. You can then see that the V's all cancel. So what we're left with is 1 over total resistance is equal to 1 over R1 plus 1 over R2. So if we do that calculation with our example at the top, R1 is 22,000 ohms, so we've got 1 over 22,000, and we've got 1 over 47,000 here. That comes to 69 over 1034. But this value here gives us 1 over RT. So you have to do the reciprocal to get the actual RT. So you have to flip it up the other way to get RT. So that'll be, I'll just move this down a bit. Okay, RT is equal to 1034 over 69, which is 15,000 ohms. So the equation for resistors in parallel is given by 1 over RT is equal to 1 over R1 plus 1 over R2, and then you carry on for how many you've got. You've got to remember to flip it up the other way when you get to the end. You will have to do some questions which have got series and parallel together, so you just have to figure out which one to do first. Sometimes it's the series one, sometimes it's the parallel one, but in the questions that I want you to have a go at, you can see. So in this one, you need to figure out the parallel bit first, and then you do add the series bit on. So if you want to calculate the total resistance between A and B, you do parallel bit and then the series bit. If you want to have a go at it yourself, you can press pause and do that now, or you can, if you want to work through it with me, you can do it on the next slide. So this is how you do it. You need to do the parallel bit first and then add it to the series bit. So the equation for parallel resistors is 1 over RT is equal to 1 over R1 plus 1 over R2. Okay, so we've got 1 over 400 plus 1 over 400, which is 2 over 400. To get RT, we do the reciprocal of that, so flip it upside down. So we get 400 divided by 2, which is 200 ohms. So these two resistors in parallel, 200 ohms. Then we've now got this bit, which is in series with these two. So you add them together. So you've got 200 here, and then add it to the 25 here, you get 225. Okay. Right, the very last bit, just want to quickly have a look at is, it seems a bit random that it's here, but I guess it's to do with that resistance thing. It's just that if you've got a heating element, then you need to provide power to it to heat up. So the potential difference across the component carrying the current is equal to V equals IR. The power supplied to the component is P equals IV, which is given in your data booklet. You can, if you use this equation and rearrange it in various forms, you can get P equals I squared R or V squared over R. So you just use whichever one of these you've got. So if you've got current and potential difference, you use this one. If you've got current and resistance, you use this one. And if you've got potential difference and resistance, you use this one. So the power supplied to the component will be the rate at which energy is being supplied to the element. So here are the elements, okay? The energy is being supplied to those elements, and we call that power. The rate of energy supply is called power. If the element remains at a constant temperature, so then the element doesn't change, then energy is being supplied to the surroundings at that rate too. So all the electrical power you're putting in this element, all the energy you're putting in, is being dissipated to the environment at the same rate. So this maintains a temperature. If you were providing more energy here than you could get rid of, then it would heat up. And if you were providing less energy here and it was radiating more, it would cool down. Because energy is power times time, you can then substitute this equation, you can use this equation and then just times it by time and you get IVT. Although I like to remember it as ITV. It's helpful. You can also substitute in this equation here, so you get I squared R times T. You could also do this one, so you'd get V squared T over R. It's a really simple substitution, and if you get a question like it, just see what you've got and pick one of these to substitute your values into, and if it wants energy, then just multiply it by the time. So I want you to have a go at the summary questions on page 219. I will send you the answers to this the next time I set you some work and how to do each one. But if you struggle with it, please let me know and I will give you a hand. Okay? Thanks. Bye.